In the previous video, we talked about why DevOps engineers should care about AI infrastructure. We discussed about GPUs, Kubernetes, MLOps, and AI system running in production. But before we deploy anything, before we scale anything, we need to understand what we are actually running. Because most engineers think machine learning is just a model. It's not. A production machine learning system started long before the model and continue long after it. And that's what we are going to break down in this particular video. By the end of this video, you will understand how machine learning differs from traditional software, how machine learning behaves differently, why data is so important, and how models are deployed in the production system. So let's get started. To understand machine learning properly, let's start with something you already understand very well, that is traditional software. Because in traditional system, we write rules. Input goes in, code runs, output comes out. For example, if input is 2, output is 4. And the most important thing is the same input will always give the same output, and this is called deterministic behavior. So this works perfectly when you can define rules. But what if the problem is too complex to write rules for? How do you write rules to detect fraud or recognize objects in an image or recommend videos on YouTube? And that's where machine learning comes in. Because machine learning does not work using rules, it works using data. So instead of writing logic, we give the system examples. So first we have a data. This is the historical information. Then we train a model. Training means learning pattern from the data, and training is usually the most computationally expensive part of the system. This is where GPUs often becomes important. And then we get a model. A model is simply a representation of those learned patterns. And then comes the inference. This is where we use the model to make prediction. And finally we get output. So instead of writing rules, we let the system learn the rules. So the system learns patterns from the data. But how are these models actually used in the real production environments? So the first way is batch inference. Here we process a large amount of data at once and generate predictions in the bulk. This is usually done as a scheduled job. For example, analyzing all the transactions at the end of the day. And the second approach is real-time inference. And in this, a user sends a request goes through an API, the model makes a prediction, and the response is returned immediately. For example, checking for fraud the moment a payment happens. So the training is usually performed occasionally, but inference runs continuously. And this is important because most production systems spends their lives performing inference, not the training. And we will dive much deeper into this in the next video. Now here's something that makes machine learning very different from traditional software. And here let's take a fraud detection as an example. In traditional system we define rules. If the amount is greater than 5,000, if IP address is suspicious, if user behavior looks suspicious, the system evaluates the rules and gives the answer that is fraud or not fraud. But machine learning works very differently. Instead of explicit rules, the model learns pattern from the data. And when we ask the same question, is this transaction fraud? The model doesn't retain certainty, it returns probabilities. So if it is fraud, that is 87%, or if it is not fraud, that is 13%. And this is the key difference because machine learnings are not deterministic. They are probabilistic. They don't tell you what is correct, they tell you what is likely. So if machine learning is based on learned patterns, what happens when those patterns change? So first of all, data goes into the training. Training creates a model and the model defines the behavior. Now imagine changing the training data completely. The code remains exactly the same, but the model learns something different and the output changes on the basis of the changed data. So if you retrain the model, you may get slightly different result. And even the randomness during the training can affect the final model. So in machine learning, changing data is like changing code. That's one of the most important ideas in this entire field. Now let's connect everything we learned so far. In traditional system, code defines behavior, we write logic, and logic determines the output. But in machine learning, data defines behavior, data goes into training, training creates a model, and model defines how the system behaves. So if the data changes, the model changes. If the model changes, the behavior changes. So if your data is wrong, your model will be wrong. If your data is biased, your predictions will be biased. In machine learning, changing data is like changing code. And this is where things become interesting for DevOps engineer. In DevOps, we version code, we track releases, we monitor deployments. But in MLOps, we also version dataset, we track experiment, and we monitor model performance. Because data isn't just input anymore. It directly affects your system behavior. And that's exactly why MLOps exist. So let's quickly recap. Traditional software follows rule. Input goes in, code executes, and we get deterministic result. The same input produces the same output. But machine learning works very differently. Instead of writing rules, we provide data, the system learns pattern, and those patterns becomes the model. And that's why machine learning is not just a model, it's an entire system. It learns from the data instead of following hard-coded rules. It produces probabilities instead of guarantees. Unlike traditional software, data becomes part of the behavior of the system. And once these models move into the production, new engineering challenges appear. We need infrastructure, we need observability, we need deployment strategies, and that's where MLOps enter the picture. Now that you understand the machine learning pipeline, you are ready for the most important concept in AI infrastructure, that is training and inference. One teaches the model and other delivers the predictions to the millions of users, but the infrastructure requirements for each are completely different. In the next video, we will break down why training consumes massive compute, why inference demands low latency, and why Kubernetes becomes the foundation for the modern AI platform. If you found this video helpful, hit like, share it with your friends, and subscribe for more content like this. Thanks for watching. I will see you in the next one.